So am I audible? Hello?
Yes, sir.
Okay. So we'll start the paper. The paper is general physical chemistry, and the first part of the paper, in this paper we'll discuss about the thermodynamics. And the thermodynamics is again divided into two parts. The first one is chemical thermodynamics, and the second one is statistical thermodynamics. So first let us discuss about the chemical thermodynamics. We have already studied the chemical thermodynamics in our graduation level. So first here we will discuss about the spontaneous process. We know that according to thermodynamics, all the chemical processes are divided into two types. The first one is spontaneous process, and the another one is non-spontaneous process. So here you can see the spontaneous process is that type of process that occurs on their own under a given set of conditions. And sometimes the spontaneous process again divided into two types: the process which will occur on its own and do not require any type of initiation, and the second type of spontaneous process is the process which require initiation. After that it will continue automatically, but initially initiation is required. And again, coming to the non-spontaneous process, so the non-spontaneous process are those physical processes which require continuous force to carry out the process. That means if we stop the any type of external supply of force, then the process will stop. So here we will discuss the criteria of spontaneous processes, right? So criteria, what is the criteria to process to be any thermodynamic process to be spontaneous? So in the graduation level, you have studied that internal energy and enthalpy, all these thermodynamic parameters you have already studied, but internal energy and enthalpy cannot predict the spontaneity of a process. So after that you have also studied as internal energy and enthalpy cannot predict the spontaneity of a process. This led to introduction of a new function that is called entropy, and certain that could serve as a criteria for spontaneity, but not to be used effectively. So in the graduation level you have studied about internal energy and enthalpy, but internal energy and enthalpy cannot predict the spontaneity of the process. And also you have studied another thermodynamic function that is called entropy. So the entropy somewhat serves the criteria for a spontaneity but cannot be used effectively. So in this chapter we will discuss what is the perfect criteria for spontaneity of a process. Now, before going to that, first we should discuss about the Clausius inequalities. So, this is one type of long question. So, first we will discuss Clausius inequalities. Now, let us consider two processes taking place between some initial and final states. Now, this is the two processes. Initial state is state 1, and the final state is state 2. From initial to final state, the process can be carried out by two different ways. The two different ways are A and B. So, so this is a very simple figure. From this figure, you can know that the process carried out from initial state to final initial state 1 to final state 2 by two different routes. We assume that one of these processes takes place under reversible condition and the other can take place under irreversible condition. So here we should assume that out of the two routes, one route will be carried out under reversible condition and another route can be carried out under irreversible condition. Both reversible and irreversible conditions you have already studied from intermediate and graduation levels. So some internal energy, and also we know that internal energy, enthalpy and entropy, all these are state functions, and state function, path functions you have also studied. So since internal energy is a state function, the change in internal energy of this process will be equals to du reversible equals to du irreversible. That means, so this is suppose path 1 and this is path 2. So out of the two paths, we have studied that, so the system changes from state 1 to state 2 by using these two routes. So out of these two routes, we have assumed that one route is reversible condition and the another one is irreversible condition. So just wait 1 minute. Yes. So out of the two routes, we have already assumed that one route will carried out under reversible condition and the other route under irreversible condition. And again, we know that internal energy is a state function. So the change of internal energy of these two conditions should be same, because we know that according to the rules of the state function, the change of internal energy in the when the process will carried out in the two processes will be same. So let us the route 1 is carried out under reversible condition and route 2 carried out under irreversible condition. So the change in internal energy in route 1, that is called du reversible, and the change in internal energy under route 2, that is when the irreversible carried out under irreversible condition, that is called du irreversible. So as internal energy is a state function, so du reversible equals to du irreversible. And again you should remember the first law of thermodynamics. According to first law of thermodynamics, we know that du equals to dq plus dw. So the terms in the first law of thermodynamics, we can write that dq reversible plus del q reversible plus del w reversible equals to del q irreversible plus del w irreversible. So this equalities we have taken from this condition. So the this condition is because as the change in internal energy is a state function. So from this condition we can write, because according to first law of thermodynamics, we know that du equals to del q plus del w. So from this equation 1.1, we can write, in place of du reversible, we can write del q reversible plus del w reversible, and in place of du irreversible, we can write del q irreversible plus del w irreversible. So now rearranging this expression, we can write del q reversible minus del q irreversible equals to del w irreversible minus del w reversible. So where del W represent the work done on the system, and you also know that work done on the system is positive, because according to chemical thermodynamics, so we assumed that when work done is on the system, then we consider that positive work, and when work done by the system, we consider that negative work. And as here work is done on the system, so that is the positive work, and its magnitude during the reversible process is greater than during the irreversible process, and hence we can write the magnitude of work done in the reversible process is greater than the magnitude of work done in the irreversible process. So the magnitude of dw reversible is greater than the magnitude of dw irreversible. Now rearranging the above equations, we can, from this equation we can write this one, that is dw irreversible minus dw reversible is greater than 0. Now substituting this equation in equation 1.4, 1.4 means this one, where we have written that del q reversible minus del q irreversible equals to del w irreversible minus del w reversible. If we put this value or substitute this equation 1.6 in equation 1.4, we can write dq reversible minus dq irreversible is greater than 0. Now, so this is equation 1.7. So if we will divide equation 1.7 throughout by t, we can write del q reversible by t minus del q irreversible by t, that is greater than 0. And also we have studied that del q divided by t, that will give rise to another function that is called change in entropy. So ds equals to del q reversible divided by t. Now putting this values of ds in equation 1.8, we can write ds minus dq irreversible by t is greater than 0, or also we can write ds is greater than dq reversible by t. Now combining the expression of the entropy change during reversible process and irreversible process, so this the equation 1.9 represent the entropy change in the reversible process, and equation 1.10 or 1.10 represent the entropy change during irreversible process. Now, if we will combine both the equations, we can write ds greater than equals to dq by t. So this is equation 1.11, and the equation 1.11 is called as Clausius inequalities. So this expression will be used in the future. All of you understood? Hello?
Yes, sir.
Yes, understood.
So now coming to the next one, that is the combination of first law of thermodynamics and second law of thermodynamics. We have already studied the first law of thermodynamics, that is du equals to dq plus del w. And let us coming
Sir,
to the second
Clausius,
law.
sir, Clausius law ର ହେଇଟା last expression ଟା ହଉଛି final expression ତ ds greater than
So
equal to
this is,
dq by
yes, this equation 1.11, that is called Clausius inequalities, and this equation will be applied many times. बहुत माने आगु को बहुत गुडे थर अप्लाई हबो दिस इक्वेशन, बुझि पाइल त?
ଆଜ୍ଞା ଆଜ୍ଞା ଠିକ ଅଛି।
So this equation is
ନାଇଁ
so
ସାର୍
that
ଏଇଟା
is
ଏତେ ଜଣା ପଇଲାନି ତ final expression ଏଇଟା ବୋଲି ନା ହେଇଲାଇ ପଚାରିଲି।
ds is greater than equals to dq by dt. So so this expression 1.11 or 1.11, that is called Clausius inequalities, right? So derivation of this equation is also one long question, so that you can find in your term and examination. Derive the Clausius inequalities, right? And this expression will be applied in future. Now coming to the combination of first law and second law. So if you combine the first law and second law, so that will give rise to fundamental thermodynamic equation. So now according to first law, you know that du equals to del q plus del w. So after that we will move to the second law. So consider a case of a closed system containing gas having constant composition which undergoes a reversible change in such a way that only work of expansion is permitted. That means we have taken a condition work of expansion only. Since we are considering a reversible expansion, opposing force would be equals to pressure of the gas. Therefore, we can write. So if we consider work done in a reversible expansion condition, we can write dw reversible equals to minus pdv. So here this is the negative work, because so that is one type of expansion work. When the system will undergo any type of expansion work, then that is called work is done by the system on surrounding, and hence in that case the negative sign will be given. Now again from equation 1.9, we know that del q reversible equals to t del s, del q reversible equals to tds. So if we will combine equation 1.12 and 1.13, So if we combine both the equation, we can find that du equals to TdS minus PdV. So this equation is called fundamental thermodynamic equation. du equals to TdS minus PdV. So this is the fundamental thermodynamic equation. Now again we will move to criteria for spontaneity of a process. In the graduation level, you have studied that entropy may be a criteria for spontaneity of a process, but here we will discuss that although entropy is a criteria for spontaneity of the process, but its utility is limited utility. So as we cannot apply entropy as the criteria of spontaneity of process always, why you cannot apply. So here we will discuss why there is a limited utility of entropy change that is applied for the criteria of spontaneity, and as we cannot apply always entropy change as a criteria of spontaneous process. So we will discuss another two different functions that will perfectly explain the criteria for spontaneity of any process. So here we will discuss why entropy change has limited utility for criteria for spontaneity of a process. Now let us consider any arbitrarily spontaneous process that is predicted by the following expression, and spontaneous process, so that is also irreversible process. So we know that any arbitrarily irreversible process or spontaneous process, del S system plus del S surrounding, that is equals to del S total or del S universe is greater than 0. This expression we have proved in the intermediate level. That means the entropy change of the whole universe is gradually increases. As the entropy change of the whole universe is continuously increases. Why continuously increases? Because we know that all the naturally occurring processes are spontaneous process. As the naturally occurring that means any type of process occurring in our universe, that means naturally occurring process, all the naturally occurring processes are spontaneous process. And again we have studied that for spontaneous process, the total entropy of the universe is gradually increases. And again we know that entropy is nothing but randomness of the system, that is the measure of randomness of the system. That means gradually the whole universe is continuously distributed randomly. That means some disorder will be there. That is the disorderness of the whole universe is continuously increases. So for irreversible process or for spontaneous process, the total entropy of the universe, that is the del S universe, is greater than 0. But if we consider reversible process, the total entropy of the universe, that is del S universe, that is del S system plus del S surrounding, equals to 0. In other words, we say that for an isolated system, the total entropy of the universe increases if the process is irreversible process, and remain constant for a reversible process. It never decreases. If the process will be irreversible process, the entropy of the universe continuously increases, and if the process is reversible process, then in that case del S universe equals to 0. So that means entropy of the process, if that will be so reversible process, entropy change will remain constant. So from this we know that the entropy never decreases. If the process is reversible process, it will constant, and if the process is irreversible process, entropy change will increase. And as all the naturally occurring processes are irreversible processes, so the total entropy of the universe, that will del S universe, is greater than 0. That means entropy of the universe is continuously in the state of in increasing state. So now coming to what is the criteria for spontaneity and for equilibrium. So here we will define a new function, that is that is called Helmholtz energy change, right? So here, using this new function, we should discuss the criteria for spontaneity of any type of thermodynamic process or the criteria for equilibrium of any type of thermodynamic process. So in chemistry, the processes, that means in chemistry, processes means mainly we are dealing with chemical reactions. The processes are carried out under constant temperature and constant pressure. So that means if you will do any type of experimental work in your laboratory, the process will carried out at constant temperature. Suppose you will do any type of chemical reactions using beaker on your laboratory table. So in that case, the process will carried out at constant temperature and constant pressure. That means at atmospheric pressure. And accordingly, we have two functions to predict the spontaneity of a process depending upon the reaction condition. Let us begin with the processes carried out under constant temperature and constant volume condition. So first we will discuss the processes which are carried out under constant temperature and constant volume condition. And in that condition, we will deduce a function that act as a criteria for spontaneity of such cases. So that means here we will derive the criteria of spontaneity of a process that is carried out under constant temperature and constant volume conditions. So we will derive the law. So this is another long question. The criteria of spontaneity of process carried out under constant temperature and constant volume. So in order to derive this criteria, or in order to derive this condition, we should consider again the first law of thermodynamics. According to the first law of thermodynamics, a process involving only so in the first law of thermodynamics we have studied that the process where only mechanical work will be carried out, and the change in internal energy according to the first law of thermodynamics can be given as du equals to del q minus pdv. Let us consider the process where uh, only heat flow is taking place between the system and surroundings. So this is the first law of thermodynamics, which explains only the mechanical work. Now we will discuss the process where only heat flow is taking place between the system and surrounding, and no mechanical work will be involved. So if we will discuss only mechanical work, and if the system, in the system there will be no expansion or no compression, then the mechanical work will be considered to be zero. So here in the first case we will discuss no mechanical work is involved. It implies that in this case the volume is kept constant. If the volume of the system is kept constant, then no mechanical work will be involved in the system, as no mechanical work is carried out on the system or by the system. So only we will discuss only flow of heat between the system and surrounding. So if no mechanical work is involved, in the other sense, we can tell that if the volume of the system is kept constant, that is dV equals to 0, so we can write the first law of thermodynamics can be written as du equals to del q. That means if system the volume of the system is kept constant, so the heat flow or the heat exchange between the system and surrounding only used to change of internal energy. If heat is flowing from surrounding to the system, then internal energy of the system will increase, and if heat is flowing from system to surrounding, then internal energy of the system will decrease, and here dV equals to 0. So if we put the Clausius inequalities for a spontaneous flow of energy between the system and surrounding, because this is the Clausius inequalities. So if we consider the Clausius inequalities in this condition where no mechanical work is involved and the volume of the system is kept constant, we can write, so from the Clausius inequalities we can write, so this is the Clausius inequality, that is ds is greater than equals to del q divided by t, or we can write tds is greater than equals to del q So this is equation 1.19, and if we put and if we combine and as the dv equals to 0, the first law of thermodynamics is converted into du equals to del q, that is equation 1.18. Now if we combine both the equations, we can write du is less than equals to tds, or du minus tds is less than equals to 0. Since internal energy U and entropy S are state functions, a combination of the two state functions will also be a state function. So here we are mentioning from equation 1.18 and equation 1.19, we are finding that du minus tds is less than equals to 0, and here we will include the Clausius inequality conditions. So du minus tds is less than equals to 0. So here u is the internal energy, that is a state function, and S entropy, that is a state function. So the combination of the above two state functions will give rise to another new state function, and let us the new state function is A. So here we are defining the new state function as A. So A equals to U minus Ts. Here A is called a new state function, that is called Helmholtz function. And since the unit of internal energy and the unit of Ts, that means the dimension of internal energy and the dimension of Ts are in energy. So the unit of internal energy is the unit of energy, and unit of Ts has the unit of energy, and hence the unit of A, that is similar to the unit of energy. So the SI unit of the Helmholtz function A is Joule. As this is one type of energy term, we can call the Helmholtz function to Helmholtz energy. Understood? Hello?
Yes, sir.
Okay. So the new function, we have defined the new function, that is called Helmholtz function or Helmholtz energy, that is A equals to U minus Ts. And if we take the differential of the new function or the new function, that is Helmholtz function or Helmholtz energy, we can write dA equals to du minus Tds. So here we take the differential at constant temperature condition. So the equation 1.12, if we take the differential of equation 1.21, that will become dA equals to du minus Tds, that is called equation 1.22. So again, if we combine the equation 1.20, 1.20 means this one, du minus Tds is less than equals to 0. So that is equation 1.20, and 1.22 is dA equals to du minus Tds. So if we combine both the equations, we can write, or if we compare both the equation 1.20 and 1.22, we can tell dA at constant temperature and constant volume is less than equals to 0. We had initially assumed for a spontaneous heat flow at constant volume and have applied at constant temperature condition. So initially we have assumed that. Thus the equation 1.23 provide a criteria for spontaneity and equilibrium of a process taking place at constant volume and constant temperature. Because initially we have assumed that the process carried out at constant volume and constant temperature, because in laboratory whatever you will do, so that is generally at constant volume and constant temperature condition. So thus, under the condition of constant volume and constant temperature, a process will be spontaneous if it will accompanied by decrease in Helmholtz free energy. So here we will find the criteria for spontaneity of a process which is carried out at constant volume and constant temperature, because most of the reactions what we are doing in the laboratory, that is at constant volume and constant temperature condition. So thus under constant volume and constant temperature condition, a process will be spontaneous if it is accompanied by a decrease in Helmholtz free energy. That means del A is less than 0 or dA is less than equals to 0. So del A is less than 0 or dA is less than 0. So that means if change in Helmholtz energy or Helmholtz energy is less than 0, then the process will be spontaneous. And it will continue and would be continue till there is a decrease in Helmholtz energy. And that is a spontaneous process, and the process will continue spontaneously if until decrease in Helmholtz energy, until there is a decrease in Helmholtz energy. That means until the condition will be applied del A less than 0, up to that the process will be spontaneous. But when a state of minimum Helmholtz energy will reach and there is no further decrease in Helmholtz energy, that means the Helmholtz energy will continuously decrease and the process will be spontaneous. And one state will come, there will be no further decrease in Helmholtz energy. So in that condition, del A equal to 0, then the process will become equilibrium. So this is the criteria of spontaneity and equilibrium of a thermodynamic process. So this is one criteria, and similarly we will define another function is there. So according to the Helmholtz free energy, so if there will be decrease in Helmholtz energy, that means if del A is less than 0, the process will be spontaneous and the Helmholtz energy will be continuously decreased. And when there will be a condition reached, the Helmholtz energy will not further decrease. So in that condition, there will be no change in Helmholtz energy or no change in the value of A. So then del A will be equals to 0 and the process will be at the state of equilibrium. And again, we will move to equation 1.22. So the equation 1.22, that is dA equals to du minus TdS. So if we apply a finite change condition, we can, so this is the change. If there is infinitesimal change, we can use differential term. But if there is a finite change, we can use del term. So for infinitesimal small change, we can use d term. So the equation 1.22, that is dA equals to du minus TdS, can be changed into del A equals to del U minus, that means both the forms are same. The first form is for very small change, that is infinitesimal change, and the second term is for finite change. So for a finite change, the equation 1.22 can be written as del A equals to del U minus T del S. So, for a finite change taking place at constant temperature and volume, the criteria of spontaneity and equilibrium is given as, so the criteria of spontaneity is del A is less than 0. This is the criteria of spontaneity, that is del A less than 0, and the criteria of equilibrium, that is del A equals to 0. So the criteria for both spontaneity and equilibrium is given by del A at is less than equals to 0. And here we have assumed that the process should be carried out under constant temperature and constant volume. So that's why we can write the equation 1.25 to be del A at constant temperature and volume should be less than equals to 0. Now moving to the condition for spontaneity and equilibrium. So here we have discussed about the criteria for spontaneity and equilibrium, and again we will move to the condition for spontaneity and equilibrium of thermodynamic process. So the equilibrium, the equation 1.24, that is del A equals to del U minus T del S. Equation 1.24, and if we combine equation 1.24, that is del A equals to del U minus T del S, and the criteria for spontaneity and equilibrium, that is del A is less than equals to 0. That means if we compare 1.24 and 1.25 both the equations, we find out the spontaneity of a process at constant temperature and constant volume depending upon the combination of change in internal energy and change in entropy of the system. Thus, for a spontaneous process, del U minus T del S should be less than 0, and for equilibrium process del u minus t del s should be equals to 0. And there are several different combinations of so here del u is the change in internal energy, T is the temperature, that is constant temperature, and del S is the change in entropy of the system. And there are several different combinations of internal energy change and entropy change possible for a given process. So we will discuss the several different combinations one by one. So first we will discuss case 1. In the case 1, suppose del u is less than 0 and del s is greater than 0. Del u is less than 0 and del s is greater than 0. And here this is the condition for spontaneity of the process, that is del u minus t del s should be less than 0. And if del u is less than 0, that means the value of del u is less, and del s is greater than 0, then the value of del s is more. Then definitely the process will be spontaneous process, because if the value of del u will be less and the value of del s will be more, one negative sign is there, so the overall value will be negative. So in this case, the value of del u minus t del s will be negative for all temperature, because this is a very high value. This means means del s. The del s value is high and the del u value is low. So at all temperature, the total value of del u minus t del s will be negative, and hence the process will be spontaneous at all temperature. That means here under case 1, we have discussed if the change in internal energy is less than 0 and if the change in entropy is greater than 0 at any temperature, whatever may be the value of the temperature, the process will be spontaneous. So this is condition 1. Now coming to the condition 2. So in the condition 2, if del u is greater than 0 and del s is less than 0, so here the equation is del u minus TDS, del u minus T del S. The equation is del u minus T del S. Now if the value of del u is greater than 0, that means this is positive value. And the value of del S is less than 0, that means this is negative value. And one another negative sign is there, so negative of negative, that will become positive. So the total value of del u minus t del s will become positive, that is greater than 0, and in that condition the process will never spontaneous. Understood? Hello?
Yes, sir, understood.
Yes, sir.
Okay, sir.
Okay. So now coming to the case 3. So case 1, when del u less than 0, del s greater than 0, the process will be always spontaneous at any temperature. Case 2, when del u greater than 0, del s less than 0, the process will never be spontaneous, whatever be the value of t. Now coming to condition 3. So in this condition 3, del u is less than 0 and del s is less than 0. In this case, del u will be less than 0 means this value is negative. Del u value will be negative, and t del s value will be positive because del s is less than 0. So del s value is negative and negative of negative, so that will become positive. So at certain temperature, the magnitude of this value will be equals to del u. The magnitude of del u equals to magnitude of t del s. So in that condition, del a equals to 0. So at that condition or at that temperature, at this temperature, the system will be in the state of equilibrium. So when the system is in the state of equilibrium, del A equals to 0, and we know that the this total value equals to del A, and that is equals to 0. That means del U equals to T del S. So we can write T equals to magnitude of del U divided by magnitude of del S. Now coming to condition 4. So in the condition 4, if del u is greater than 0 and del s is also greater than 0. If del u is greater than 0 and del s greater than 0. So if del u greater than 0 means this value will be positive. and del S greater than 0 means total this value will become negative, because minus sign is there. T del S will be positive and del U will be positive. So in that case, if the change in internal energy will be more positive, then the process will be non-spontaneous, and if the change in entropy will be more positive, the process will be spontaneous. So that is condition 4. So according to the condition 4, if del U is greater than 0 and del S will be greater than 0, in this case both del U and del S terms will be positive. Hence again a certain at a certain temperature the magnitude of this term, both the terms will be equal. So in that case del A will be equals to 0. So when the magnitude of both the term means when the magnitude of del U is equals to the magnitude of T del S. So in that case del A equals to 0, and that is the condition of equilibrium. But when some
Sir,
other
del eta kono?
hello
Del eta kono?
देखो del A already ଆମେ ଏଠି discussion କଲେ, that is called Helmholtz function A ହେଲା ଗୋଟେ new function। ଆମେ ଏଠି criteria spontaneous process ପାଇଁ ଆମେ ଗୋଟେ new function define କଲେ, that is called Helmholtz function। ଆଉ ଯେହେତୁ ତାର ୟୁନିଟ ଟା ବା ତାର ଭ୍ୟାଲୁ ଟା ଏନର୍ଜି ରେ ଆସୁଛି, ତ ସେଇଟାକୁ କୁହାଗଲା Helmholtz energy। so that is called A, and A is also a state function। so del A is the Helmholtz energy change between the two states. Del A is Helmholtz energy change between the two states. That means if the system will carried out from state 1 to state 2, so that means if the system will change from state 1 to state 2, so del A is the change in Helmholtz energy between the two states. Understood?
Thank you, sir. Thank you.
Okay. Now, so if del A equals to 0, the process will be at equilibrium, and here some other conditions will there. The process will be spontaneous only when the magnitude of del U will be less than T del S. If the magnitude of del U will be less than T del S, then the total value will be negative, and del A is less than 0, then the process will be spontaneous. And the process will be not spontaneous or non-spontaneous if del U will be the value, the magnitude of del U will be greater than T del S. The process will be non-spontaneous. Now coming to case 5, where del S equals to 0. So in such cases, the process will be spontaneous only if the process will be exothermic. So here del S is equals to 0 means this term will be completely 0. So the criteria of the process only depend upon the change in internal energy. And in that condition, if the process will be exothermic process means if energy will be released from the system, then the internal energy of the system will decrease. So del U is less than 0. In that condition, that will be spontaneous. But if there will be no change in internal energy of the system, the process will be equilibrium. Now now coming to the case 6, where del U change in internal energy will be 0. So if change in internal energy will be 0, only this term will be there, minus TdS term will be there. So when minus TdS term will be there, if the process will be spontaneous only when del S is greater than 0. So if del S is greater than 0, that means when del S is positive, T del S will positive and minus T del S will become negative, and the process will be spontaneous. And if del S will be less than 0, that means the value of del S will be negative, T del S will be negative, but minus T del S will be positive, then the process will be non-spontaneous. But if del S will be equals to 0, the process will be equilibrium. So this table completely describes the criteria of, you can easily understand from the table the condition of spontaneity, completely describe the condition of spontaneity and equilibrium for different combinations of del U and del S. So all the conditions we have already discussed, 1, 2, 3, 4, 5, 6 cases we have already discussed, and the summary of the 6 cases is given in this table. You can find out that. And now coming to one example, the example is very easy example. You can solve the example using this del A, this equation, that is del A equals to del U minus T del S. Now coming to the physical significance of Helmholtz energy. That means still we are discussing about the Helmholtz energy. So that means A, Helmholtz energy A. So here we will discuss the physical significance of the Helmholtz energy. According to equation 1.22 that we have already studied, so dA equals to du minus dds. And again, if you will so remember the first law of thermodynamics, du equals to del q plus del w. And from equation 1.13, that is a system undergoing reversible process according to second law of thermodynamics. If the process will be so reversible process, we know that del q reversible equals to TdS. So combining the above three expressions, that is the expression of first and second law that we have already studied. So this is the combined expression of the first and second law, that is du equals to TdS, du equals to TdS plus del W, that is the reversible work. Here this is the reversible work, del W reversible. And if we substitute this, the combination, the equation of the combination of first and second law in equation 1.22, if we will substitute this equation in equation 1.22, we can write dA equals to TdS plus del W reversible minus TdS, because equation 1.22 state that dA equals to du minus TdS. So here in place of du we can write TdS plus del W reversible minus TdS. Now that will become dA equals to del W reversible. This is equation 1.31, and this equation describes the change in Helmholtz energy is equals to work done during isothermal reversible process. If the process will be isothermal and reversible process, then the change in Helmholtz energy term, that is dA, equals to work done during the reversible condition. And the value of W reversible will be negative, indicating that work is done by the system. If work is done by the system, then the work is negative work. Therefore, decrease in Helmholtz energy equals to the work done by the system during isothermal reversible process. This work includes all type of work that the system can do. Thus, Helmholtz energy change is relative to the maximum work that can be obtained from a system, and hence that is also called as work function. So here we have from equation 1.31, you can see the change in Helmholtz energy is deals with the change in reversible work, or the so reversible work done by the system. That's why the Helmholtz energy term is also called as work function, because the Helmholtz energy change is completely relative, so related to the maximum amount of work that can be done, and hence the change in Helmholtz energy, that is dA, is called work function. And here we have discussed one criteria for the spontaneity of the process, and the complete summary you can find in the table 1.1. And we have also discussed all the things mentioned in the table by case 1, case 2, case 3, case 4, and case 5, case 6. All these so discussions are here summarized in table 1.1. So that deals with the criteria for spontaneous process, and that is called Helmholtz energy, and also that is called the change in Helmholtz energy is also called as work function. Now coming to another new function which will also describe the criteria of spontaneous process. Let us consider heat flow taking place between the system and surrounding spontaneously at constant pressure. Here we are considering at constant pressure. At that time, we have considered at constant volume and constant temperature. Here we are considering at constant pressure. So when constant pressure condition will be there, we will move to Gibbs function. When constant volume condition will be there, we will move to Helmholtz function. So here we'll discuss the spontaneous process, the exchange of heat between the system and surroundings spontaneously at constant pressure. So when we'll discuss about the spontaneous process at constant pressure, we should define Gibbs function. For constant volume, we should define Helmholtz function. So when the system and surrounding heat is flowing between the system and surrounding spontaneously at constant pressure, and such a heat flow is equal to change in enthalpy of the system, because as the pressure of the system is constant and heat is flowing between the system and surrounding, so whatever the heat, suppose if heat is flowing from surrounding to system, then the total enthalpy of the system will decrease, and if heat will flow from system to surrounding, then the total enthalpy of the system will be decreased. So heat flowing between the system and surrounding at constant pressure deals with change in enthalpy of the system, and let the amount of heat exchange between the system and surrounding at constant pressure, that is del qp. So here subscript p is there, that means pressure is constant, so that is called del qp. So this amount of heat exchange between the system and surrounding at constant pressure, that is completely equal to change in enthalpy of the system. So del H equals to del QP. dH equals to del QP. That is equation 1.32. And again, if we apply the Clausius in, so similar derivation will be there. For Helmholtz function, we have also applied the Clausius inequality. And here for Gibbs function, if so here for Gibbs function, if we apply the Clausius inequality here, so the Clausius inequality, that is TdS is greater than equal to del Q, that is equation 1.33. If we combine both the equation, we can write TdS is greater than equal to del H. And this equation can be rearranged. dH minus TdS is less than equals to 0. dH minus TdS is less than equal to 0. That is called equation 1.35. So this equation 1.35 holds for a process taking place under constant temperature and constant pressure condition. Since the left hand side of the equation is a combination of two state functions, so we know that enthalpy is a state function, entropy is a state function. So as the left hand side of the equation represent the combination of two state functions at constant temperature, temperature is still constant, then the total expression of the left hand side gives rise to another new expression, that is called Gibbs function, and also this is one type of energy term, and hence that is called Gibbs energy. So the Gibbs energy G, that is represented as G, so it can be so represented as G equals to H minus Ts. Since enthalpy H, Ts, both the terms having the unit of energy, G also will have the unit of energy, and hence that is called Gibbs energy. So similar way, what we have discussed, Helmholtz function was called as Helmholtz energy, and similarly Gibbs function is also called as Gibbs energy. And the SI unit of Gibbs energy is Joule, and for very infinitesimal change or small change, the Gibbs energy change can be written as dg equals to dh minus tds, that is equation 1.37. So equation 1.35, this one, equation 1.35, that is dh minus tds less than equals to 0. So that is the criteria for spontaneity of the process. So that is less than equals to 0. So this equation holds good. Equation 1.35 is valid for the processes taking place under constant temperature and constant pressure. Exactly similar expression we have studied, where the process will be carried out under constant temperature and constant volume. If the process will be carried out on constant temperature and constant volume, we have written the equation del dA equals to du minus dds. So in that case, A was Helmholtz energy or Helmholtz function. And here if we compare this equation, in place of A, we have written G. And in place of internal energy U, we have written H. Because in the previous condition, the process was carried out under constant temperature, constant volume. And in this condition, the process is carried out under constant temperature, constant pressure. So when the process will carried out at constant temperature, constant volume, then Helmholtz energy term was used for then Helmholtz energy term was used to define the criteria of spontaneity of the process. And if the process will carried out at constant temperature and constant pressure, then Gibbs energy term will be used to define the criteria of the spontaneity of the process. So both the equations are exactly similar. Only at constant volume condition we will use A and we will use internal energy U. But at constant pressure condition, in place of A we will write G, that is called Gibbs energy, and in place of U you will write H, that is called enthalpy. So similar explanation you can find out. So Gibbs energy change of the system is less than equals to 0. From both the equations, we can write dg at constant temperature pressure is less than equals to 0. And if you remember, suppose we will go to that one for Helmholtz function, you can find out this one. Exactly similar condition we have derived. Here we have derived that del A at constant temperature and volume less than equals to 0, and here you will find del G at constant temperature and pressure less than equals to 0. This one, dG at constant temperature pressure less than equals to 0. And similarly we will discuss Gibbs energy, that is the criteria of spontaneity of a process. While deriving the criteria of spontaneity of process occurring under constant temperature and constant pressure, there we have deriving the criteria for spontaneity of the process which are occurring under constant temperature and constant volume. Here we are deriving the criteria of spontaneity of the process occurring under constant temperature and constant pressure. Both the derivations are exactly similar. Only the difference is constant volume Helmholtz function or Helmholtz energy, for constant pressure Gibbs function or Gibbs energy. For constant volume A, that is del A or dA, for constant pressure G, that is dG or del G. So under constant temperature and constant pressure condition in terms of Gibbs energy, we also use Clausius inequalities both for both of the conditions. It implied that we had taken into account both reversible and irreversible process. There also we have considered both reversible and irreversible process. Let us take the reversible and irreversible process separately. Here we will discuss the reversible and irreversible process separately. And for Helmholtz function, we have also discussed the reversible and irreversible process separately. So for the reversible and if we discuss the reversible and irreversible process separately, then according to equation 1.13, that this equation we have used while discussing about the Helmholtz function, and similarly same equation also we are using here, TdS equals to del Q reversible. So this is the condition of reversible. And again if we move to equation as per equation 1.32, if we move to 1.32, this one, dH equals to del QP. So if we compare, if we put this value, we can equation 32, just we are writing equation 1.32 here. So that is dH is equals to del QP, and if we combine both the equations, that is 1.13 and 1.32, we can write del H equals to T del S, or del H minus T del S equals to 0. And here enthalpy is a state function, entropy is a state function, so the and temperature is constant. So the combination of both the state function gives rise to another new state function that is called gives free energy change, that is dg equals to 0. So in place of dH minus T del S at TDS, we are writing dg. Now, for an irreversible process, TDS is greater than del Q irreversible. Now, substituting this value, we can find out dg less than 0. So, if dg is equals to 0, if dg is less than 0, the process will be spontaneous. That means if dg is negative, the process will be spontaneous and also irreversible. And if dg equals to 0, the process will be in the state of equilibrium, and that is reversible. Now, coming to the relationship between spontaneity, Gibbs energy, and entropy of the universe. We know that for any type of spontaneous process or for any type of irreversible process, the total entropy change of the universe is continuously increasing. That is, ds is greater than equal to 0. And for an isolated system, ds will be equals to 0 if the process will be reversible, and ds will be greater than 0 if the process will be irreversible. So this is the combined equation, that is ds is greater than equals to 0. We know that generally a system interacts primarily with with the surroundings. Thus, the system and the immediate surrounding can be assumed to be isolated from the rest of the universe. Such a system is said to be composite isolated system. And for that system, the total entropy change of the system is given by the expression, that is del S total equals to del S system plus del S surrounding. Since surrounding are much larger than the system, then the gain or loss of energy by heat the surrounding is taken as a reversible process, and irrespective whether the actual process is reversible or not. That means the change in entropy for the surrounding always reversible, because the surrounding is far larger than as compared to the system. So therefore, we can write ds surrounding equals to del q surrounding divided by t, which is equals to minus del q system divided by t. That means this amount of heat is released by the system to the surrounding. So the total heat in the system decreases. That's why for system one negative sign is there. And as this amount of heat is released from the system to the surrounding, so in case of surrounding, positive sign is there. So ds surrounding equals to del q surrounding divided by t, which is equals to minus del q system divided by t. And we know that at constant pressure, del q system equals to dh system. So when the pressure will constant, the change in energy of a system is the change in enthalpy. So if we'll put this condition here, del q system divided by t, we can write ds total equals to ds system minus dh. So in place of del q system, we are putting the value dh. So the equation can be written as like this: ds total equals to ds system minus dh system divided by t. And again, if we simplify this equation, we can write ds total. Here you will take LCM as t, so that will become ds total equals to tds system minus dh system. And here this term will equals to dg. Dg means change in Gibbs energy. So ds total equals to minus dg system divided by t. Since ds total decreases for a spontaneous irreversible process, therefore for spontaneous process at constant temperature and constant pressure, we can write minus del g system is less than 0, minus del g system is greater than, minus del g system by t is greater than 0. That means del g system is less than 0. So this is the desired criteria for spontaneity of a process at constant temperature and constant pressure. Exactly same type of conditions we have studied the desired criteria for spontaneity of a process under constant temperature and constant volume, that is dA system less than 0. So when the process is carried out under constant temperature, constant volume, the criteria for spontaneity of the process was dA system less than 0. But when the process will carried out under constant pressure and constant temperature and constant pressure, this is the criteria of spontaneity of the process, that is del G system less than 0. That means the value of del G system should be negative. So, and so this is for infinitesimal change or very small change, and for a finite change we can write del G at constant temperature and pressure less than 0. Exactly similar equation we have also written for finite temperature, finite change, that is del A at constant temperature volume. So in that case T and V was there, and here del G at constant temperature pressure less than 0. So this is the criteria for spontaneity of the process which is carried out at constant temperature and constant pressure. And exactly similar derivation we have studied the criteria for the criteria for spontaneity of a process carried out at constant temperature and constant volume was like this: T, V less than 0. This both the equations are exactly same. Both the equations are same. And if del G at constant temperature and constant pressure equals to 0, then the system is at equilibrium condition. And for finite change at constant temperature and constant pressure, the Gibbs energy can be written as del G at constant temperature and constant pressure equals to del S minus T del S. And similarly, the condition of spontaneity and the condition of equilibrium for a process carried out under constant temperature and constant volume can be summarized in this table. Similar value will find, and also here 6 cases are there, exactly similar definition you can find out. After that, coming to the example 1.2, so that is a direct numerical, you can find out that. Now coming to physical significance of Gibbs energy, because we have studied that Gibbs energy G equals to H minus Ts, and substituting this the value of uh, and we also know that H equals to U plus PV. Now substituting the value of enthalpy in this equation, we can write G equals to, in place of H we are writing the value H equals to U plus PV. So we can write G equals to U plus PV minus Ts. Now if you take differential of this equation, right? So the left hand side will become dg and the right hand side will become du plus pdv plus vdp, because here pv term is there, so that will become pdv plus vdp, and again here ts term is there, so that will become minus of tds plus sdt. So so that will become minus tds minus sdt, and hence the differential equation of equation 1.53 will become dg equals to du plus pdv plus vdf dg equals to du plus pdv plus vdp minus tds minus sdt, that is equation 1.54. And again you recall from above by combining the expression of first and second law, we have already studied this. So this is the combination equation of first and second law, that is du equals to TDS plus del W reversible. Now if we substitute the value of du in this place in this equation, we can write dg equals to TDS plus del W reversible plus PdV plus VdP minus TDS minus SDT, and hence you can see this TDS term will be cancelled out. So we can write dg equals to del W reversible plus PdV plus VdP minus SDT. And if the process will carried out at constant temperature and constant pressure, so if we are because we are already defining for Gibbs free energy change or Gibbs energy change, the process should be carried out at constant temperature and constant pressure. So when the process will carried out at constant temperature and constant pressure, dt will be equal to 0 and dp will be equal to 0. So these both the terms will become 0. So we can write dg equals to del W reversible plus PdV. So here del W reversible is the total work done on the system under reversible condition at constant temperature and constant pressure. Why we are telling the work done on the system? Because here positive value is there, so that's why we are considering work done on the system, that is positive work. If work is done by the system, then negative sign will be there. So this can include all type of work like electrical work, chemical work, mechanical work, and also pressure volume work. So you know that the mechanical work is nothing but work of expansion or work of compression, that is called pressure volume work. So if you consider pressure volume work here or only mechanical work here, so in this in the place of dW reversible, and if expansion, and if you consider expansion, then dW mechanical, that is equals to minus PdV. So here in the equation 1.54 we have derived that dg equals to del W reversible plus PdV, but mechanical work of expansion can be written as del W mechanical equals to minus PdV. So in this place we can write, in place of plus PdV we can write minus del W mechanical, and hence the equation will become dg equals to del W reversible minus del W mechanical, that is 1.58. So here del W reversible minus del W mechanical is a non-expansion work, and we call the net work done under reversible condition, and hence this is nothing but del W reversible minus del W mechanical. So why that is called non-expansion work? Because we have already defined that del W reversible may be mechanical work, may be electrical work, may be chemical work, but here we are deducting the mechanical work part, because mechanical work only deals with the pressure volume work, so that is the expansion or compression work. So when you will remove mechanical work part from complete work, so this work del W reversible minus del W mechanical will become non-expansion work, because del W mechanical is expansion work. Here we are removing expansion work or mechanical work from the total work, and hence this the this term of work is called a non-expansion work. We call, and hence we call net work under reversible condition. And if we write dg equals to del W reversible minus del W mechanical, that is equals to del W net reversible. And you know that the work done by the system, if negative sign is there, so if work is done by the system, then there will be negative sign. So in that case we will write minus del G equals to minus del W net reversible. If work is done on the system, we can simply write this one. If work is done by the system, we can write this. So here we have discussed the criteria for spontaneity of the process, which can exactly define the criteria for spontaneity of the process at constant temperature and constant volume condition, and in another condition at constant temperature and constant pressure condition. We have already discussed at constant temperature and constant volume condition, the energy term was considered to be Helmholtz energy, and similarly at constant temperature, constant pressure, we have derived a new term that is called Gibbs free energy. So now we will find out the relationship between Gibbs energy and Helmholtz energy. So from this equation 1.36, we have defined G equals to H minus Ts, and again putting the value of H, we can write, so this is the value of H, that is U plus PV. So if we put the value of H, G equals to U plus PV minus Ts, and again from Helmholtz condition, we have studied that at equation 1.21, we have studied A equals to U minus Ts. So from this equation, we can write this one U minus Ts, and hence the equation 1.53 can be written as G equals to A plus PV. So gradually we are finding the relationship between Gibbs energy and Helmholtz energy. So this is the relationship between Gibbs energy and Helmholtz energy, that is G equals to A plus PV. But this relationship can be changed when the system will change from one state to another state. So we will derive the relationship when the system will move from state 1 to state 2. Let the initial state of the system in the rate of change of Gibbs energy, the rate of change of Gibbs energy with temperature and constant pressure is equals to decrease in entropy, and similarly the rate of change of Gibbs energy with pressure at constant temperature is equals to increase in volume. Now coming to, let us take up the variation of Gibbs energy with temperature and constant pressure. So here we will discuss the variation of Gibbs energy with temperature at constant pressure, because at constant pressure term we are using Gibbs energy. So this is the variation of Gibbs energy at constant with temperature at constant temperature, the variation of Gibbs energy with temperature at constant pressure, and the equation is called as Gibbs Helmholtz equation. This is another one long question. So see, from equation 1.69 we can write dg equals to del g by del t at constant solve this equation in a very simple manner. In order to solve this equation in a very simple manner, we take the function g by t, we will consider the function g by t and differentiate the function with respect to t at constant p. And hence, we can write del g by t divided by del t at constant pressure is equals to this. So if you compare equation 1.76 and 1.77, the RHS of 76 is the negative of RHS of 1.77. Both are similar, only one negative sign is there. And hence, the LHS of 1.76, that is h by t square, equals to minus of this. So just we are writing that one. Del G by T by del T at constant pressure equals to minus H by T square. This is equation 1.78. So the equation 1.78 is called Gibbs-Helmholtz equation. This is one long question. Now coming to variation of Gibbs energy with pressure at constant temperature. Here we have discussed variation of Gibbs energy with temperature and constant pressure. Now we'll discuss the variation of Gibbs energy with pressure at constant temperature. Coming to equation 1.70, this one, we will take this term, variation of Gibbs energy with pressure at constant temperature. So simply we can write del G by del P divided by T, which is equals to V. Del G by del P at constant temperature is equals to V. Therefore, we can write dg at constant temperature equals to vdp. So dp term will move to RHS. To find the total change in Gibbs energy with respect to change in pressure, we need to integrate this equation 1.79. If we integrate this equation 1.79, if we integrate this equation 1.79, so if we integrate this equation 1.79 from initial Gibbs energy G1 to final Gibbs energy G2, and when the pressure changes from P1 to P2, the integral from of equation 1.79 can be written as integration of dg from G1 to G2 equals to integration of VdP from P1 to P2. Since the volume varies with change in pressure, it take inside the integral. So this equation 1.80, the value of equation 1.80 can be written as G2 minus G1 equals to V whole into P2 minus P1. So this is equation 1.81. From this expression, we can conclude that for solid and liquid, there is an increase in Gibbs energy with increase in pressure. Because for solid and liquid, the volume is constant. On the other hand, in case of gases, we cannot assume that the volume is constant. So the volume is constant when the reactant and pressures all are in solid and liquid state. So in that case, we will consider volume as constant. But if we are dealing with any type of reactions of gaseous substances, whether in reactant side or product side, we cannot assume that volume is constant. So we need to use a relationship between volume and pressure. So as for gaseous substances, the volume is not constant. So this equation is valid for liquid and solid substances. But for gaseous substances, in place of V, we can write V equals to nRT by P. So this is from ideal gas equation PV equals to nRT. So in place of V, we can write V equals to nRT by P, and putting these values in equation 1.8. So and and solving the value of equation 1.80, the integration, the equation will become G2 minus G1 is equals to integration of nRT by P dP from P1 to P2, and that is equals to nRT ln P2 by P1. So just here you will see that nRT all are constant. So in this equation, nRT all are constant. So that is the integration of dP by P. We know that the integration of dx by x, that is ln x. So the integration of dP by P will be ln P. And as the limit will be there, the integration of nRT by P dP from pressure P1 to P2. So putting the limiting values from P1 to P2, we can write G2 minus G1 equals to nRT ln P1 P2 by P1. So this is equation 1.83. And again, as the pressure is increased, that is P2 is greater than P1, the right hand side of the above equation will be greater than 0. That means as the pressure will increase, this value will greater than 0. Hence, for ideal gas, Gibbs free energy change increases with increase in pressure. And we know that an ideal gas under isothermal condition, again we know that P2V2 equals to P1V1. So this equation can be written as del G equals to G2 minus G1, that is equals to nRT V1 by V2. And using this equation, you can solve example 1.3. And similarly, coming to the next part, that is temperature and volume dependence of Helmholtz free energy. So this derivation is exactly similar to temperature and pressure dependence of Gibbs energy. Here this is temperature and volume dependence of Helmholtz energy. In the previous part, in the just previous class, we have discussed temperature and pressure dependence of Gibbs energy. So exactly similar derivations you will find out. So you can see exactly similar expressions are there here, and here you will find the Gibbs, the second form of Gibbs Helmholtz equation, exactly same form. So that was the first form of Gibbs Helmholtz equation. In the other sense, you can tell Gibbs Helmholtz equation in terms of Gibbs energy, and this equation is the Gibbs Helmholtz equation in terms of Helmholtz energy. So there are two different types of Gibbs-Helmholtz equation. One is Gibbs-Helmholtz equation in terms of Gibbs energy, and the other one is Gibbs-Helmholtz equation in terms of Helmholtz energy. So this is the Gibbs-Helmholtz equation in terms of Helmholtz energy. You can see exactly we have derived the same equation. This one. So this is 1.78, that is the Gibbs-Helmholtz equation, and similarly you will find 1.96, that is also another form of Gibbs-Helmholtz equation. So both the derivations are exactly similar, and these are two different long questions. Now coming to variation of Helmholtz energy with volume at constant temperature, similar type of derivation. So in that case, we have discussed variation of Gibbs energy with pressure at constant temperature. Here, variation of Helmholtz energy with volume at constant temperature. Exactly similar type of derivation was there, and exactly for gaseous condition, all the derivations are same. And after that, some examples are there based upon this Gibbs-Helmholtz equations, both forms of the Gibbs-Helmholtz equation. Now coming to the next one is Maxwell's relationship. The Maxwell's relationship are differentials, partial differential equations. So the Maxwell's relationship will be derived from four different thermodynamic equations. So the four different thermodynamic expressions are there, based upon internal energy, based upon enthalpy, based upon Helmholtz energy, based upon Gibbs energy. Because we have studied that du for internal energy is a function of entropy and volume, enthalpy is a function of entropy and pressure, Helmholtz energy is a function of volume and temperature, Gibbs energy is a function of pressure and temperature, and these are the four differential terms of. So this is the first differential term, that is differential term of U, internal energy. So that is U equals to TdS minus VdP, and this is dH equals to TdS plus VdP, dA equals to minus PdP minus SDP, and dG equals to VdP minus SDP. And all the 16 Maxwell's relationship will come from these four equations. So the Maxwell's, so if you remember these four equations, so the Maxwell's relationship will be very easy for you, because so all the 16 relationships of Maxwell's equations will be derived from these four equations. So that part we will discuss tomorrow. And okay, hello,
Okay, sir.
is there any
Okay.
doubt? Hello, any doubt? No. Okay, you just go through what we have studied today. You go through your study material and also solve all the numericals what are given in the study materials. So if you face any type of problem, so then we'll discuss tomorrow. Okay.
Okay, sir.
Okay, sir. Thank you, sir. Thank you.